In a previous video, I talked about giving LLMs read-only memory. I allowed them to access any conversation from a history, which effectively gives them infinite memory. Today, I'm going to talk about giving LLMs read-write memory, and this will allow me to do two things. First of all, have a chat with an LLM that remembers my name and other personal details, and second of all, read documents in much the same way as humans would, which means reading through chapter by chapter, taking notes, and being able to compare notes from those in the past. By means of a brief recap on the previous video, the whole idea here is to set up local memory for the LLM, which consists of its context or words that it sees. And second of all, have disk memory, which is really a database where we can store contents that are not within the context, but are available to be retrieved. And then we set up processes that allow the LLM to write to this disk memory and then read back from that memory. Now, this is exactly how we split up the context in the previous video. So the context has got a portion for the system message, a portion for read-only retrieval. I'll recover that in a second. There's space for the recent chat history, so a certain number of turns actually defined by number of tokens. There might be enough to fit, say, the 5 last turns of conversation or 10 turns, depending on what size you allocate for this recent chat history. And then there needs to be enough space for the LLM response. Outside of the local memory or the chat context, there are conversations from the past. In fact, all conversations that are stored on the disk, which is really just a database. I stored it in JSON. Probably at scale, you would store it in Postgres. And this is just a database of all of the history. And the LLM now is allowed to access only its most recent conversations within the context. So the oldest conversation gets kicked out as we keep adding new ones on here. But if it wants to retrieve older conversations, the LLM is able to retrieve from this conversation history, which is automatically stored as we kick out conversations. And the LLM can do that by making a query, a search query with some keywords, and then the relevant turns of conversation from the past that best match those keywords will be placed inside this read-only portion of memory. So there are two things that we're going to build on or add to this pipeline today. The first new feature we'll add in is read-write memory. So here we'll add a new block to the local memory or context, a new allocation for what we call read-write memory. And the LLM is able to issue a command that says certain text should be written, essentially stored within this conversation block here. And that allows the LLM to do a few things. First of all, it could simply record the name of the user, like I'm talking to Ronan, so it knows that in the future it's talking to Ronan. Or it can also help for taking notes during long processes like reading documents where you're just reading chapter by chapter, but you want to remember what you saw in chapter 1. And that'll be a core part of the document reading that we see in a bit and that we're covering today. Now, if you do introduce a read-write block, there is the question of how you manage that context, because the LLM might keep on writing more and more notes, and eventually this context will get full. And there are a few ways to handle that. So first of all, you can simply just drop the oldest memories using a first in, first out type of approach, or FIFO or FIFO. And this works well. In fact, we're going to do it today. The problem is it can drop information that you would like to persist. For example, if the LLM knows my name is Ronan, you probably don't want that dropping off the edge of the cliff. You want it to kind of stay there. So first in, first out works well for recent memories or kind of short-term memory, but the LLM would have to keep on writing to it if it's to remember some information that really should be more persistent. So as an improvement, and I won't complicate the model today doing this, but I'll describe it. As an improvement, you can do periodic summarization. So when the local memory gets full, if this block here, say it has 10,000 token allocation and it's actually, because you will just measure when it's going to go right over that. Instead of allowing it to overflow, you'll make a new call to the LLM and you'll ask the LLM to either summarize it or, even better, ask it to create a rewrite, to rewrite the memory, maintaining the most pertinent parts that should be persisted. And so in this way, it probably would choose to keep information like the user's name is Ronan, but it might choose to drop or to summarize some of the other information. So as I said, we're going to go with the simple approach today. We're just going to do first in, first out. And if you have a big enough context, and if you have just one kind of long task, this may be enough. You may not even reach a point where it starts to overflow. Now, the second feature, I said there were two features we'd add today. The first is this read-write memory, but the second feature is adding a document database that we're able to query. Just like we have a conversation history that we can query, we're now going to have a document database, which again will just be a JSON file for today, but in practice, in production, you would set it up as a Postgres database, maybe using the approach I've described in some of my videos before. Now, while the conversation history is automatically populated from the recent chat history, the document database is something that we will have to populate ourselves before running the agent. We will, in other words, upload or process documents to be stored in a certain format within this database that I'm going to describe in a little bit. While in principle now you could have the LLM write or append to the document database, we're going to make this actually a read-only database. So the LLM will be able to make queries, but we're not going to allow it to write in the first place. So for today's video, I'm just going to make this database read-only, and I'll do the same in the next slide here. I'm going to make it read-only. So the LLM is allowed to make queries to the document database. And I'm going to talk about two query types. The first is it will be able to search, do a keyword search. And the second is it will be able to read certain lines of the documents it specifies. So it'll have the ability to both search and read portions of the documents. And when it does either of those, that content is going to be placed within the read-only box over here within its memory. So the only thing it can write to is its local memory here, the read-write memory. It's not able to write to this document database for now, although you could think of scenarios where it might make sense to allow it to do that. We're just going to allow the LLM to query based on search and based on kind of reading a specific number of lines. So with that said, let's think about how the agent or the assistant or the LLM should be able to read documents. And there are a few ways you can think about doing this. The first is you could simply make the read-only memory big enough so that it fits full documents. So if you make this box here, say 30,000 tokens in size, or 100,000 or using Gemini, maybe 1 million or 2 million, you could in principle retrieve a full document and read all of that document in one go. The problem is reasoning of LLMs, even if they're very long context LLMs, tends to degrade after somewhere like maybe 20 to 30,000 tokens. So you're going to start losing performance in terms of reasoning. Even though a needle in a haystack may be perfect, the LLM's able to pick out specific info from anywhere in the document. That doesn't mean it's able to do the more complex task of reasoning between parts in the document. So for that reason, just taking a read-only approach with a very large context often won't give the best reasoning results. The next approach is to do search and retrieval. So like any kind of RAG pipeline, you can retrieve specific chunks based on keyword search. And doing that will work for a lot of queries. If you have specific questions, it can work quite well. The problem is if you want to reason over a whole document or ask a more vague question like, which parts of this should I improve? Or what are the inconsistencies overall in this document? There isn't an easy way to just do that based on search and retrieval. And so you probably need a way to be able to read any part or every part of the document. And so that leads us to option 3, which I propose as the solution here. And that's to let the LLM or the assistant read documents like a human. Now, how do we let an LLM read like a human? I propose 3 different steps. First, providing a document database. No surprise there. Second of all, the ability to search. And by search, I mean the simplest form of search, ctrl+f on any document combined with pagination. So when you do ctrl+f on a document, it searches, but not only does it search, you can often keep clicking next to see every instance throughout the document. That's what I mean by pagination. And we'll find when you provide that, it gives a pretty exhaustive way, especially when the LLM can change its search query. It gives it a very precise way to target information in the document. And last of all, and perhaps most importantly, the LLM needs to be able to read specific lines out of the document. For example, specify this document lines 1 to 100, and then those are returned and placed within the read-only context window right here. Combining all of these tasks is going to allow us a tool or a setup whereby the LLM is able to read just like a human. Now, I'll briefly mention, sorry, this is a bit of a sidebar, but there is a slightly alternative approach you could take here with a document database and just a read function. And actually, if you just allow an LLM to read, based on pages, let's say pages X to Y, like 1 to 5 from document Z, if the documents have a table of contents, the assistant will usually find that table of contents and then figure out which page to navigate to. Now, for this to work, it requires that your document be formatted in terms of pages, which may or may not be trivial depending on the starting point of your doc. It also requires that your document be well written and laid out and have a table of contents, which not every document does have. So this technique will work. It's kind of interesting. It does, but it's not as fast as having ctrl+f available as a tool for the LLM, where it can precisely query and then find the lines where those keywords are and then read around those lines. Something I want to say about search, I see it as a spectrum. So on the one hand, you have ctrl+f. Then on the other hand, you have vector search. Vector search is where you break chunks or pages of your document to be represented by arrows, and then you look for the similarity of direction between an arrow representing your query and representing your document, and that's how you find the closest chunks. BM25, meanwhile, is somewhere in the middle. It's basically keyword based. It allows you to find the keywords within the query that are rare within the documents and then find the documents that have those rare keywords. So it's an advanced form of keyword search. And the way I think about this spectrum here is between one of semantic relevance and granular control. If you do ctrl+f, it's literally going to match that string. If I put in dog and I misspell it with 2 G's, it's not going to find dog anymore. Whereas if I put in semantic relevance, it's going to be a lot more smoothened in the paragraphs that it finds. Whereas semantic relevance or vector search will find passages or pages, ctrl+f will find words or locations, whereas vector search will find similar results. Even if you tweak the word of the search or the query by a little bit, you'll still get similar semantic results. On the other hand, if you tweak just by a letter the search in ctrl+f, you're going to get very different results. And this actually has pros and cons because it means you definitely get more semantically relevant results using vector search, but you can get very precise granular control using ctrl+f. So you can target these very small words or phrases and paginate through exactly where they appear in the document. Actually, it can end up being true that if you do have multiple shots available, which agents do, then using multiple shots in pagination, you can end up doing better by using ctrl+f. Whereas if you must get the most relevant result in one shot, you're probably going to be better off using something like vector search and BM25. So what I'm proposing is, if you're getting an agent to search, consider allowing them to have tools just like humans, which means give them ctrl+f and give them the ability to read and to paginate as well. So in this video, we're at the end of the presentation part now, thankfully. I'm going to set up and test local memory, and not just local memory, but local read-write memory by setting user preferences. So I'm going to get the LLM to be aware that it's me, Ronan, talking to it. And I'm then going to set up a document database and start making a specific query to see if the LLM is able to use ctrl+f plus reading to answer it. And then I'll start to collaborate with the assistant in order to read a longer document and get it to generate kind of a list of running commentary or inconsistencies as we move through section by section or chapter by chapter. Now, something you'll realize if you saw the first video is that I don't actually use tool calls or function calling here. I do tag-based commands. So when there's a command the LLM needs to make, it will do so within XML type tags like this, search doc. And this, it's just a more flexible way to make commands that's quite concise, and it avoids having to lock into a specific format of tool calling that might limit you to a certain LLM or not. This approach is just defined in the system prompt and it's agnostic to whatever LLM endpoint that you use. It should work the same as long as the model is good at instruction following. Now, for the demo part of this video, I'm going to run through working with this agent on 3 tasks. And I'll be using the scripts from advanced-inference, which you can get over on trellis.com. This is a paid repo. You can get lifetime or you can get annual access to it. If you're not able to afford the scripts, I will try to describe at a high level what I'm doing, so at least you could replicate my approach by yourself using something like ChatGPT or Cursor. So I've git cloned this repo into Cursor, and you can see I have the repo open here with all of the folders. There are many, many scripts included within this repo, all the way from setting up servers, doing sampling, like speculative decoding techniques, running Monte Carlo, doing fact-checking, DSPY. But we're focused on memory. It's the same repo that we used for the first video on memory. And in fact, if you open up the README, you'll see that there's a branch now, git checkout read-only memory, if you want the exact scripts from the first part of the video, because I've now merged in the changes from this new part of the video into main. And so that's what we're seeing here on the screen. Now, I'm going to describe my task.md file. This is the file I use to build the full app. And I have a new section added on for today's functionality, which covers the two things we're going to add, which is the read-write memory and the document database. So I'll go through this section in a bit, but it's more intuitive if I just run, first of all, the three examples I want to run for you. And if you're first time into this repo, if it is your first time, you'll want to run pip install uv, then you'll want to run uv pip install -or requirements.txt. And this is going to fail because I need to cd first into my memory folder, then run the install. I've installed everything already, and then uv run main.py, and we should be up and running with our chat. So with the chat running, you'll see already in the UI that I have access to two documents. How does the agent know this? Because the available documents in the database are being put in the system message. So this assistant always knows which documents are available in the database and how many lines are in each document and how many tokens. And there are two documents in it right now, which I can find. In fact, you can include any number of documents by putting the PDFs in this documents folder. I've got one on the rules of touch rugby, and I've one on this speech-to-speech model called Moshi. Now, to convert these into MD files, which is the format I want in order to inject lines of the markdown, MD for markdown, into my LLM when I need it for the calls, I use a package called Marker. Now, Marker's not totally permissive, but if you have under 5 million in revenue per year, I think you can use it for free. And also there's an endpoint where you can pay just per document, I think, or some other basis if you don't want to run the models locally. But you can run the models locally. That's the way I have it set up myself. And so when I run uv run main.py, it runs the script Marker in order to convert these documents into MD. And actually I've stored MD copies here. You can see here's an MD version of the rugby one, and it really is quite beautifully rendered. Even the images are cleanly extracted. And you can see here, for example, look how neatly this table is parsed. This is all markdown here. So the quality of the Marker tool is excellent. It's a lot better than, say, PyMu PDF for LLM, which is a tool that also goes from PDF to markdown. So I highly recommend this tool, and it's what I use to generate the documents. The documents go in the database, and then they can be queried via search by querying lines of the markdown, and also the LLM is able to read specific line groups that it specifies. So here we are with Jimmy. Jimmy says hello. I've said in the system prompt, the assistant's called Jimmy. I'll say howdy, I'm Ronan. And Jimmy now says, hi Ronan, it's nice to meet you. I'm your personal assistant. And Jimmy writes to local memory that the user's name is Ronan. And the effect of this is that when I go to the conversation history, you'll see this 3-turn chat here. If I just delete it and save, and now if I exit that chat and start a new chat, Jimmy says, hello, I'm Jimmy. I say howdy, I'll just say howdy. Howdy, Jimmy, even spelled incorrectly. And Jimmy says, hi, Ronan, even though this time I didn't say anything in my conversation history. And the reason why is because this time around, Jimmy has got access to the read-write memory, and my username has been stored from the last turn of conversation. So this is a quick demo of how Jimmy is writing on the earlier chat to local memory. The local memory now contains this memory, and therefore Jimmy is referencing it quite nicely, I would say. Okay, so for the next test, I want to ask the LLM or the assistant for help reading a document. And I'm going to ask for how much a try is worth using a fresh conversation. So I've deleted here the conversation history. And note, for the purpose of memory management, I'm working here with a context of 5,000. It's a pretty short context. All language models pretty much today can handle that. I'm allowing 500 tokens for the read-only memory. That's where search results or lines to read from the documents go. 500 tokens for the read-write memory. That's for notes or for customer or user preferences. 500 for my user messages, which will be short, and 250 for user messages and 500 for my response. So I'm going to run the program by cd into memory and then uv run main.py. And you can see Jimmy has access to 2 documents. And I'm going to say, what docs have you access to? Just to double check the info in the system message is coming through, which it seems it is. And I'm going to say, yes, find out how much a try is worth in the rulebook. And so Jimmy's going to search first for try worth points. And Jimmy's clearly not happy because he tries another search term, try points. And then he's still not happy. So he says, let's search for try and then search for points. So he's breaking it into single words. So he looks for try, doesn't get any results, presumably, looks for scoring. And here it looks like Jimmy has found something in search results because he's able to read the document now and specifically read pages 358 to 365. And with that, it looks like Jimmy has found that a try is worth 1 point. Jimmy decides to commit this to local memory. And there is a warning here that we've reached the maximum number of tool calls or tag calls. So I've set that maximum to 5 turns. I'm just going to say, yes, we can continue. And yeah, it looks like Ronan, I found the information in the rulebook. A try is worth 1 point. So let's just check some of the logs to see it matches with our understanding. In the read-write memory, it looks like a try is being 1 point is being written to memory. And if we go to the latest prompt here, we can maybe see a history of the read-only local memory. So I'm scrolling down and this is still all the prompt. Until now, we should get to the read-only local memory. And you can see the document portion with lines 358 to 365. And these are the lines Jimmy is asked to read. And indeed, the scoring lines are contained right here. Now, if we go back to previous loops, so previous prompts, we should be able to see what information was found in those earlier searches. And again, we'll go to the read-only memory. This one here is the same information because Jimmy basically provided 2 final responses when he called the right memory and then when he provided the final response. So I need to go back 2 turns. And here, if I move to the read-only memory, you can see some history saying there was a search for scoring, and that did return 1 page with 8 matches, and it returned a line saying scoring, which isn't of particular help, but probably more usefully, it found a line that is the heading of a section called section 14 scoring. And when Jimmy knows that that section is on line 358, that's most likely how Jimmy decided to go ahead and make a read of the lines from 358 through to 365. So what I'm showing you here is that if you give ctrl+f and you give the ability to read, the language model can, although it may take a few steps, get to answers pretty much like a human would. I think in retrospect, it would have been better for me to use BM25, or it would have been better for me to use embeddings or both, because Jimmy probably would have found the relevant information quite a bit earlier rather than having to cycle through these different attempts. But I think it's illustrative just to show you how, paired with simple tools, an agent is able to get to the answers you need when it's a strong model like Claude 3.7. Now, there's one more example I want to show, and that's getting Claude, in this case, or Jimmy, to help me out with reading a document. So let me go to my conversation history. I'll clean that out, cd into memory and start a new chat. And I want some help reading this document about Moshi, the speech-to-speech model. It's this document here, which is a paper from arXiv. And so I'm going to ask Jimmy for help. Can you help me read the Moshi document? I want to create a report. I want to create a report assessing each section. Okay, I mean, this is pretty vague, but let's just go with this. I'm going to say, let's read each section and take down notes about memory requirements for running this model, if any. You should move section by section and record notes at the end of each section, as well as stop and ask for my feedback. So this is something I recommend. I'm putting myself into the loop here. So I'm not allowing Jimmy to just go all the way through the document. You could try that. I think you'll find it's inconsistent in whether Jimmy makes it to the end following the rules. But if you put yourself in the loop so that every now and again Jimmy has to check back, this is probably more likely to do this. So I'm going to put this in. Jimmy says he's going to help me read through. Let's start by looking at the structure. So Jimmy starts with the abstract. And yeah, I'm going to stop this here. And I'm going to change my config so I can read more lines. Something I didn't show you before is that I've set a maximum of 10 lines that can be read at once. I'm going to increase this to 150 just to allow for more reading. I'm going to increase my context length as well, up to something that I think is probably close to optimal for any document, because if you go beyond 32,000, I think reasoning degrades. So the local memory I'll increase in size, the local read memory I'll increase in size. Actually, the read-write I'll put at 4,000 and the read-only I'll actually put at 16,000 because I want a decent chunk to be allowed within the context. So Jimmy can read decent chunks of documents at a time. Like imagine you have a document that's like 100,000 tokens long. That means Jimmy's going to need to read at least 4, 5, 7 times. So yeah, ideally you want to make this long, but on the other hand, if you make it too long, that's going to affect reasoning. So for my user messages, I'll keep them short, but for the response, I'll allow for a longer response. And by the way, this is relevant for, you'll see it in the first video, if I'm recalling from my conversation history, this is the max number of conversations per page for pagination. Okay, so let's run from main and let's just say, let's start again. And I can scroll up. Do I have any conversation history? I don't think I do. I'll just check. Yeah, it looks like I do. So I can just say, let's start again from scratch. So here, Jimmy's going to read through the Moshi document, starting off with the abstract, adding in the results. And notice that first Jimmy did a search for abstract. Then Jimmy started to read lines 5 to 15. And now Jimmy is reading through more. So reading through the introduction as well. And Jimmy also has written some notes to local memory here with respect to the first section. So I just need to find where that tag starts, write local memory, and then all of this content here on the abstract and introduction. So far, no explicit memory requirements mentioned. Okay, that's good. Let's read the second section. I'll just say the next section. So now Jimmy's going to move on and read lines 40 to 65. And now read the rest of the related work section. And seems like Jimmy's having an issue finding the end of that section. And so does some search for the word model. I'm not really sure that's the most effective way to go about it. But just by reading through lines, I think Jimmy has realized we have got section 2 complete. And so starts to write to local memory notes on that section. Okay, so still nothing on the model requirements. But we can check in the meantime what's been written here. So you'll see we have the old note of my name. We have the note from earlier on the touch rugby. And then we've notes here on the abstract and intro, as well as notes right here on section 2. And yeah, I can go ahead for one more section. And let's see what Jimmy does here. Section 3 is a bit longer, so I expect it'll take quite a few steps. Jimmy's reading lines 90 to 115. I'm now moving to section 3.2. And the key thing is that we need our 16,000 character tokens to be able to fit a full chapter. If that's not possible, that means we should have asked Jimmy to actually review by half of a chapter at a time. So here, it looks like Jimmy's continuing to read the section on model architecture, but is branching off now to try and do a search for the word parameter. I'm going to allow for extra calls here. So, okay, it looks like the summary's now been written. Let's see if that's been, yes, that's been written to write-only memory again. So you can see now we have notes on section 3. Now, I'm going to exit here and just take a look at the prompt. Let's take a look at the last prompt that we had. So I'll scroll down, check out the prompt. And in particular, I'm interested in the read-only local memory. And you can see here it's showing me lines 40 to 65. And as I move down, I'm moving to the more recent portions of text. So here now I'm starting to hit section 3, which is good. 3.2. You can see that query where Jimmy tried to search for section 2, but wasn't lucky on that. Another search here for the word model, and there are quite a few results for the word model. We should have, I think, 8 results if there are more than, in fact, no, we're allowing 10 results per page, and it looks like there's more than 2 pages of results for the word model. Looks like there are 18 pages. So yeah, it makes sense. The word model would be used a lot in that. Then we can see there's a document read from line 65 to 90. And it's hard to read Markdown when it's just printed like this. But the LLM can, of course, read this very well. And here we have more lines here. And then we have more lines again. Oh no, this is a search result. So looking for architecture to find the architecture section. And then we have search results for parameter, which you'll recall. And that's the end of the memory. So, I mean, one interesting question we could ask here is just recap your reading of section 3. Can you check you read all of the lines of section 3? Overlap is fine. Just answer that question. Don't take any new actions. And here Jimmy is reviewing, and it looks like we do have a contiguous piece going from 90 to 165, and perhaps after line 165, Jimmy is missing some content. And we can manually check that by looking at the MD files, going to Moshi here. And then if we check 165, you can see I'm really looking for section 4, 3.4, 3.1. And so, yeah, section 4 starts on line 215, which definitely suggests that the LLM has not read beyond section line 165, which just shows you that you do have to be cautious with doing this kind of review. Potentially, if we had allowed for reading more lines at a time, that may have helped. But already we are allowing for reading quite a few lines. You can see here, we're allowing for up to, I think, 150 lines. And Moshi is, or rather not Moshi, but Jimmy is currently not deciding to read that many lines at a time. Jimmy is rather reading fewer lines. So you can see here, at least with the agent being able to interact with the human in the loop, we are able to interject. But you can see it's not easy to get the model to be completely comprehensive. And so in conclusion with that demo, my main remarks would be, yes, with minimal tools, you can get an agent to help with ctrl+f and with document reading on a line-by-line basis, but probably you will speed up the iterations if you are able to provide BM25 or provide embedding type search. It will just improve the search results and remove the amount of iterations you need. And second of all, if you are going to do a longer task like document reading, you probably want to try and put a human in the loop. And unfortunately, the models are not at the point where they're going to be meticulous. You'll find cases, even when you manage the context correctly, that the language model is just not complete in doing what you've asked it to do. With those high-level demos true, I want to show you a few snippets in code of how I've implemented all of this. I'll start by describing my task.md file, where I've got the instructions I provided to build the add-on to this app. Just briefly, The additions I've made are to add read-write memory and to add a document database. Here I'm describing that in very high level. For the read-write memory management, the model is using a write local memory tag. So when it wants to write, it will call with this tag. It will put a string of what it wants to write and then close the tag. No explicit read operation is needed because the memory is already in context, so that content is put directly into the context. An archive of the read-write memory is stored on disk. I showed you that a few times. Here's the archive. And the way this works is the archive is used to populate the local memory, but only the memories that fit, the most recent ones, are included. That's why it's a first in, first out type design. The total size of the read-write memory should not exceed LRWM, which is local read-write memory, which defaults to 1500 tokens, but you saw I increased. When I want to read longer documents, you should try increase it to the max the model can reason at, which is probably around 16,000. And obviously now that we've allocated this memory, that reduces the total available memory for conversation turns, for the most recent turns, which is now reduced to the full context minus the system message, minus the local read-write memory, minus the local read memory, minus the response, and minus the user's turns as well. For the disk and database memory, I'm storing them in a JSON file. I'll show you that JSON here. It's got each of the documents, and then for each of the documents, it's got the title, it's got the content, it's also got the number of tokens, which we can see right down at the bottom, the number of lines, the path, and the last modified date. Going back to the task file here, the using marker PDF, pip install marker-pdf, we convert the PDFs into Markdown, and then they're the lines from which we query. And that's described in document retrieval. It can be called on by using the read document tag and then passing in the document name, followed by a colon, and then the start line, and then the end line. And the document search, which is currently simple ctrl+f search, it works by using search document tags and then the query. And if you do a search, or if Jimmy does a search, Jimmy can then paginate by passing in search document page, then the page number, and then search document page. And so these are the two core functions, the document search and the document reading. And these allow us to access what's on the document database. In conjunction then with the read-write management, we're able to have Jimmy write some notes on what is being read. Now, just a note before I finish on how the tag system works. Every time the LLM makes a call, which you'll have seen many times in the terminal, there are tags. There's an opening tag, a string, and a closing tag. And each of those closing tags is set as a stop token. So in chatbot.py, when I go to stop tokens, you'll see here I've listed all of the stop tokens that are possible for each of the different tag calls. And then when the LLM is called, which is being done here, LLM response stream, the stop tokens here, we have the stop tokens being passed in to stop. Now, when you pass in stop tokens, it will cause the LLM to stop generating, but it will also pull out, it will suppress that stop token from the response. So what you'll be left with is a string of text that includes a start token and then a string afterwards, but no stop token or no closing tag. So then what it boils down to is writing some code that detects that start token. And the code for that is contained here. Basically, we check what happens if the opening tag is fetch memory. Likewise, we check what happens if the opening tag is fetch memory page, write local memory, read document, search document page. And depending on which one of these is found, we then take an action on that basis. And more specifically, the process I go through is I find that there's a starting token fetch memory, there's a string afterwards, I add the closing token that was suppressed, so that gives me a string enclosed in the tags. Then I extract using a regular expression the text that's between and act on that text. Usually I'll act by adding text into the context, by adding it into the read-only window, for example, or by adding it into the read-write window. And then I will send back a message, for example, searching disk memory in the case of fetching a memory, or maybe a message like fetching page X for query from disk memory. So I'll send back that message that appears in the user, rather the assistant's message turn within the conversation. So that's roughly how all of the tags are working. Now, maybe one last thing here, just on the memory manager. This is now expanded so that we can include read-write memory, which wasn't there before. And there is a function to load read-write memory, which loads from the history of read-write memories. So that's a function that will just read the most recent ones that fit into the context. And then we also have functions that allow us to save read-write memory and also add to the current read-write memory. So when we're not processing the first turn, we're basically looking at what's already in read-write memory and then adding a new memory and kicking out an old one. So that's exactly what happens here in this add to read-write memory function. Now, maybe one last thing to look at is the system message in chatbot.py. And this message is now fairly long. It's about 20 or 150 lines in total. We have Jimmy, the personal assistant. We have the 3 types of memory: local conversation memory, which is the last few turns, the disk memory for the conversation history, and then now new, this local read-write memory. There's a list of the documents. This is how Jimmy knows what documents are available. There's the ability to search the documents and to fetch a specific page of document search results. I explain then how search works, like ctrl+f. I give some tips on working with the documents, particularly for when reading them, to only read a maximum of this number of lines at each time. I give some tips on when to search memory, like if I, as a user, ask for something that happened in the past. I explain how memory works, how results are added to local read-only memory when a query is made to the database of memories. I explain how to search memories. This is all from the first video here. How to write to memory using this new functionality from this video. That's where we write, for example, the user's name or notes on reading the documents. I include tips on searching the document database now. I include tips on working with pagination. I include some one-shot examples that always improves performance. And yeah, then I just remind Jimmy that his name is Jimmy and to be concise in responses unless told to elaborate. And that's a very quick overview of the code base for this read-write memory and document database. All right, folks, that's the review of document reading agents using read-write memory, which is handy for many other things as well. And also my overview of how you can get to a document reading agent just by having ctrl+f and allowing the document agent to read specific or query specific lines. As usual, all of the resources are available in the repo advanced-inference. That's on trials.com. And you can let me know any questions or comments right below here in the video.